Welcome back. We're going to pick up here. As we said last time, we left off with the Doppler effect. Now, the Doppler effect is a change in frequency due to the moving either of the observer or the sound source. So when sound is let out from something that's stationary, the sound waves radiate out from it in all directions at the same way. But if the thing making the sound is moving, it may be traveling towards its own sound waves, which means it's also going to be traveling away from its own sound wave. And this is why a siren sounds like it's a high pitch when it's moving towards you or a low pitch when it's moving away from you. So in this picture in your notes, it shows the police car going towards this guy, and the police car is driving towards its own sound. So as the sound waves leave, it drives towards the ones that are trying to get away from it and away from these other ones behind it. Now let's take a look at this slide. So sound travels at about 330 meters per second, or about 739 miles an hour. So if the car is going 70 miles an hour, then it's moving at about 1/10 the speed of sound. Or another way you can think about this, if the car is going 70 miles an hour, which is about 30 meters per second, then the sound is only able to get away from the car at about 300 meters per second. Okay, so the sound wave leaves the siren. It's going forward 330 meters per second. But the car is like chasing it at 30 meters per second. So it's only going to have a gain of 300 meters per second, okay? Because, if that's how much faster than the car it's going. Its speed is 330. The car is like chasing it at 30 meters per second. So it's only going to gain by the difference, 300 meters per second. Now, behind the car, the sound waves are going away from the car at 330 meters per second, but the car is moving in the opposite direction at 30. So these sound waves are going to have a difference of 360 meters per second. So they're going to be farther apart, and these are going to be closer together as the sound drives towards its own sound waves. We're going to take a look at this little animation of how the Doppler effect works. Okay, so we're going to take a look at the Doppler effect. Now, in this animation, the car is going to be letting out sound. And so we're going to see the sound traveling out in all directions from the car. And so there's the first sound wave, the second one, the third one, the fourth one. Okay, and what it's showing is the car is driving towards its own sound. So as it lets out these sound waves, okay, the car is moving towards its own sound in front of the car, so it's bunching up. Now, if the car was sitting still, the sound waves would travel out the same distance from each other in every direction. The car is moving towards the sound waves in front of it and moving away from the ones behind it. So instead of the waves being at regular intervals and spaced out evenly like this, in front of the car, each waves, the car gets closer to the one that when it lets out the new wave, and it's driving away from the old waves. So here again, we see the car is letting out these sound waves, and this is the blue one that represents where the sound would be if the car was still, okay? But because it's not still, when it lets out these sound waves, here it drives closer to the wave that it let out before, and here it's driving away. Now what this means, if there's a person standing here, when the waves get to this person, these waves are going to be closer together. And we know that closer together means higher frequency. So as the car approaches, when the sound waves from the car, like if it had a siren on or whatever sounds it was making, is the crests are closer together, they're closer to one another when they reach this person. So he's going to hear a higher pitched sound when the sound gets to him. Now, eventually, the car is going to get to the person who's the observer, and these high frequency sounds that he's hearing, okay, would be low frequency sounds on the other side as the car moves away. So the man is over here now, and as the car got past him and moves away, the sound waves that he hears are farther apart. So what he's going to hear is a lower frequency sound. So this is why the pitch, like of a train whistle, changes as the train goes past you. As it comes towards you, you hear the high frequency sound, okay, because the waves are more bunched together. And as it moves past you, you hear the low frequency sound because the waves are moving away from you. So they're farther apart, longer wavelengths mean lower frequency. This is a quick video that shows the change in pitch.
In the phenomenon known as the Doppler effect, sound waves that are approaching an observer have a higher frequency than sound waves that are moving away from the observer. This can be illustrated by the sound of an approaching train whistle. The pitch of the whistle appears to increase as the train approaches and drops in tone after it passes. This occurs because as a train approaches, the sound waves of the whistle are crowded together, producing shorter wavelengths and therefore a higher pitch. As it passes, the wavelengths increase in length and the pitch of the whistle drops. This phenomenon also occurs with stars. Stars moving away from the Earth have a shift towards the red, or lower end of the spectrum, while stars moving towards the Earth have a shift toward the blue, or high frequency end of the visible light spectrum.
Let's take a look at this slide again with the car. Suppose that the car got to the speed of sound. So the car was going 330 meters per second. So when it let out a sound wave, it was going at the same speed as the sound wave. Well, the sound wave wouldn't be able to get and travel away from the car because it would try and go 330 meters per second, and the car would be going the same speed. So they would move together. And that's what we see when we see a jet like this breaking the sound barrier. These are all those compressional waves, all those sound waves trying to move away from the jet, but the jet is going at the speed of sound. So the compressions, and this is all the bunched up compressions that we see here in the air, the compressions can't get out in front of the jet because it's keeping up with these sound waves. Not only are they closer together, but they're all compressed in one place. So here's this little video of this jet going at the speed of sound, and you can see how all of a sudden the sound waves bunch up in that compression, that cone in front of the jet. When it releases this energy, that's when we hear a sonic boom. So we're going to take a look at this little video that explains a sonic boom.
We're all used to the idea that light travels faster than sound. Think about thunderstorms. You always see the lightning before you hear the thunder, despite the fact that they both occur at the same time. Sound travels at approximately 330 meters per second, which is pretty fast. However, man has been able to beat this speed and break the sound barrier with supersonic travel. The incredible thing about breaking the sound barrier is that it not only produces an audible effect, but also a visible one. Take a look at this picture. You can actually see the effect on the air as the plane blasts through the sound barrier. Isn't that amazing? The reason why this occurs is because as the plane travels through the air, it pushes the air out of the way, which creates pressure waves that travel at the speed of sound. This is similar to the waves created by the bow and stern of a boat as it moves through the water. As the plane approaches the sound barrier, the air cannot get out of the way quick enough, and it is squashed together into one big shock wave that is travelling at the speed of sound. This shock wave begins at the nose of the plane and ends at the tail in steady flight. It forms a kind of cone shape that surrounds the plane, as can be seen here. The pressure inside the cone is not that much greater than normal air pressure. However, since this overpressure is released very quickly, it is audible as a sonic boom. Have a listen to one. There are actually two booms that are produced, one at the nose and one at the tail, which you can see in this video. However, they usually pass over observers almost at the same time, and so most people will only hear one. It's not just fighter jets that can produce a sonic boom. Perhaps the most famous form of transport that could break the sound barrier was Concorde, which was a commercial airliner before it was put out of use in 2003. Space shuttles can also break the sound barrier, but only when they re-enter the Earth's atmosphere. Well, that's all we have time for, except for this last fact. Humans are actually able to produce a sonic boom using their hands. The crack of a bullwhip is actually a sonic boom. This is because the end of it is travelling faster than the speed of sound.
Okay, now I'd like you guys to answer these questions on your own, and we'll pick up here when we come back next time. I hope you're having a great day, and we'll see you soon.